Okay, my wonderful friends. Listen, this is Roger Spur, Mud Fossil University, and today we're going to be going through physics and the atomic structure, which everybody knows what atoms are. They're the things that make everything, little atoms, and they're all different kinds. Now, if you have kids, really what I want you to do for me, and as parents, decide whether you want to do this or not, but what I would like is to know if you have 8 to 12-year-old kids, right in that range, or any kids, I don't care, I don't care how old they are, but I really specifically want to know, will they understand this in the range of 8 to 12 years old? Because as it is right now, they say nobody can understand quantum mechanics, and that's true, because it's not correct. This is the standard model right now of quantum mechanics. They say there's gigantic protons, which is like this big gigantic proton. There's neutrons like this, which is a gigantic neutron. And then there's little tiny, tiny, tiny electrons like that. And the little bitty, bitty, bitty electrons orbit these gigantic other particles. And for some reason, this negative, which is the electron, we call it a negative particle, and we know that negative slams into positive. Well, for some reason they just stay away from that positive. Nobody's ever been able to explain this, and it isn't correct. That's why. Now, the reason it stays away is because that is not one gigantic proton. That is just no more than a ball of these particles, which are the electrons. Now, we're going to go through this. It's very, very, very simple. And here's all it boils down to right here. This is the true nature of an electron. It has a negative charge, yes. That little negative charge, yes. Absolutely. Let me get my feather pointer. That little negative charge is this electron. Now, everything there is has a weight to it, which is called the mass. And then when you go in atomics things, they call it the atomic mass. And this atomic mass is 0.00005438 atomic mass units. Okay, because 1 unit is a neutron. Now, they will say, and I'm going to show you what they say in a traditional theoretical physics right now, which is wrong. So I'm going to show you they're wrong, I'm right. You decide. I'm not going to push it on you, but I'm going to show you my evidence to support 100% of what I'm saying, and they have no evidence to support what they're saying. So let's take it from there. And it doesn't make any sense at all. If that particle there has the same charge as that particle there, that's just, but opposite charge, and it stays away from it. Why would that happen? It go bang, and everybody's done. And it does. So here's what the story is. Everything is made out of electrons. All of these particles are made out of a big snowball like this, only it's all made up of these particles. It's not one big proton. It's 1,839 electrons make that proton. All right. Now, at 1,840, you have a neutron, because now you have one more, and it attracted that. Now, at this point, it has neutral value. It does not want any more electrons. So the electron normally we consider to be the one that's in the orbital spinning around outside. Normally they say this is what happens in a hydrogen. This big gigantic ball is the proton that is the center, and then there's a negative particle that's out here for some reason, doesn't go slamming into this big positive particle. Well, that's just not sensible. What happens is this gets to a point where it doesn't want any more electrons. It pushes one of them away. It says, I want to come in. It says, no, 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 you can't come in here. He says, we got all we want. And it says, no, 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 please, please, please. He says, no, you stay. I tell you what, let's work out a deal. You want to get in here? We want to push you away. How about you just stay right there? How about that? I said, well, if that's all you can do. And I said, that's all you can do, buddy. You're done. So that's it. You're in what's called a quantum stable state. This has its full complement of electrons, which is 1840, let's say. And this one says, I want to come in. It says, no, you can stay 5 little distances away. They call them angstroms. And they only are like inches, but they're tiny, tiny, tiny little bits away because you're in atoms. So 5 angstrom units, let's say. I'm just making that up. You can stay there, and that's as far as you can come in. You can't come in. Now, there's a lot more to this, but let's just start with that. And then let me show you what they say in the traditional physics. And you just saw what I claim. This is what the core of the center of the nucleus is. That means the center. And then you have the orbitals that spin around out here. Well, I say once you have just enough in here, it says, no, I don't want any more. And that's what's called the periodicity. 1839 or actually 1840 approximately. Well, I say almost exactly. 1840 makes the most stable hydrogen nucleus. And then one more electron floats around that nucleus and wants to get in, and it won't let it in because it's as stable as it can be at 1840. Then you go way up to helium. It's not just 2 protons. They throw in a couple of neutrons. By the time you get up here, you're over 7,352 electrons, something like this, I figured out. But it's thousands and thousands here. And this is the second smallest atom that exists. Hydrogen, helium, lithium. By the time you're up in here, you're into tens of thousands. And then up in here, you're into millions. So that's what these particles are. It's like gold is not 79. It's 100,000, 200,000. I don't know what it is. But this has all got to be calculated out. And this is what makes so much chemistry so interesting. There's a lot to this. So don't think you just learned everything there is just because you see the weights of these things. No. Stay with me. 8 to 12 years old, I think, should be able to understand. You may have to go through it 4 or 5 times and watch it, think about it, and then you may say, whoa, Roger, you missed this or you missed that. That's what I want to hear. And then we'll discuss it. Maybe I did. Because I missed a lot of stuff. I missed everything until I think I figured out most everything. Now, obviously, I can't get everything right, so fix me, help me. All right, let's figure it out. Now, don't forget, I have literally 100 videos or more on this photons and electrons. This one of these right here, that's an electron. I keep talking about electrons. They're not just one big ball of electron. They're one powerful electron part, and they're one dark matter part. Nobody's ever seen this before. The only reason we see this is because we crushed these photons through a venturi. And when we did, we were literally able to separate the muon, which is the dark matter. They call it boson, muon, dark matter. We'll call it what you want. It's attached to what we always considered was the only thing there was a little tiny electron. This is light. And this is nothing more than one electron here attached to another electron here, back to back, just like a bar magnet. And when they concuss in a venturi, we can actually separate them and do all the things that CERN's asking for. Turn this particle in between the two of them up to 200 times intensity, creating literally free energy. And we did it by forcing that particle to concuss at a venturi, creating the separation of the black balls from the white. Now, we're going to get into this deep because I'm trying to get 8 to 12-year-olds to understand this, and I think they will. The light came in here, crashed. We saw it come in as that box of particles, which was, hold on, I have one here, a simulation, which was like this when it entered. Only the white particles could get through here and explode going through. The black ones just get out of the way. That's why there's a lot of extra dark matter. All it is gravity. It doesn't concuss, it doesn't explode, it doesn't absorb, it doesn't emit. All it does is attract white. And that's when it comes back together here. I think they said it's like 12 millionths of a second. It reestablishes itself back into the dark matter and turns back. You know, they've seen these kind of things happen, just don't understand that they all started from electrons, and there is nothing more than electrons. So just follow this, and like I say, I really love to have some pushback to me from understanding whether this is being understood. Because I think we got to get to the kids, and you should teach them at home this stuff. Let them understand what they're saying at school. You can't get out of that, I don't think. But people are doing the homeschooling now, which is, you know, there's really nothing they're going to learn in school other than how to subtract and add and do all that kind of stuff, and read and write, and you know they'll get interaction. I'm not saying there's anything wrong with school, but we need to be able to change the way. It's not just dictated, and you, if you don't agree, they fail you, and then your life is ruined because you're smarter than them. That's the problem. I'm not kidding you. Right now, that's the story. I love you all. Just work with me. Don't forget electron flood theory. That's my theory. There is nothing but electrons. Protons are nothing but masses of electrons. The neutrons are nothing but same thing, only one more than a proton. And that's what counts for nuclear decay. They're only stable at periods of 1840 or so electrons in a mass. The vibration of them at that mass, Tesla understood it, and we could do it now with salt table experiments. And then all of a sudden they lock in at these huge quantities of salt. And it just makes an exactly perfect pattern, and it follows the patterns of what we would consider nuclear, you know, geometry. It follows the rule of 8 and everything. It's absolutely amazing, and it needs to be looked at in a different light. So until we get out of the Bohr model, which is totally wrong, and I want you to look up that. And think about electron flood theory, because I've shown it pretty good, and I can show it in much more detail. But it's so simple that the detail is not necessary. You have a black particle, you have a white particle. The black particle is dark matter, muons, bosons, whatever you want to call it. It just carries and glues back the white particles back together. The white are exploders. These are the glowers. These are the energetic particles. If we can intervene, and I'm going to make a drawing of exactly how we can subtract this energy, because it's 200 times more intense than it was here. Why can't we use that energy before it reincorporates itself? If we could harvest it out of here and then let it just sort of ease its way back in, we've used up all that energetic value, which is free. And you could do that in the size of a toaster. Put it in your car, you'd never have to stop driving. Okay, my friends, this is really going to be extremely simple, and like I said, anybody between 8 and 12 years old, I'd like to know if you have a kid that is in that range, can they understand what I'm telling them? And I think they will certainly be able to. In traditional physics, let me show you, I'm going to show you a drawing of what they say a proton is, a neutron, and an electron. I'm going to show it to you in a drawing, and then I'm going to show you what these particles would actually look like. If this was a proton, and it had a positive charge, and this was a neutron, and it had no charge at all, and then these little tiny bitty particles are electrons, and they have the same charge as a proton, which is a gigantic piece, only they're an opposite charge. It doesn't work. It's wrong. That's why nobody can understand it. So let's see what is correct. And the correctness is a ball of these electrons. And in that ball, there would be 1,839 if it was a proton. 1,840 of them would be a neutron. And that just means that it's balanced. At 1840, it's equal, 920 electrons back to back. At proton, it's missing one. It wants one more, so it's attractive to an electron, and an electron will be sucked into it. And when it gets to a certain quantity, which is 1840, it says, I have enough, I don't want any more. That is my period. That is my periodicity. That is my number, 1840. As you go up, every proton adds another 1839. Every neutron adds another 1840. So all we have is particles. There are no gigantic ones of these. There is no gigantic ones of these. There is only balls of these, and they fall into certain chunks. This is 1840 or so electrons, not one of these. They say there's one of these in that hydrogen. No, there's 1840 of these in that hydrogen. When you get to helium, they say there's only two of these. No, there's 7,350 of these. I mean, it gets astronomically huge numbers of particles. So they're talking about only like 6 or 8 or 10 or 12 little particles make up these different atoms. No, thousands and thousands and thousands. That way there you can have what's called isotopes. And I'll explain to you what an isotope is. It's just a word. It means you don't have enough electrons or you have too many electrons. And that makes it radioactive. And what does radioactive mean? Radioactive means that when you have too many electrons or too little electrons, you're going to either decay and lose one, or you're going to absorb one to become more stable. They want to be exactly at a certain number, and that number is 1840 is a neutron. All right, that's the period. That's the period. That's why they call it a periodic table. They didn't throw that word in for nothing. Periodic means every certain number of particles you add another atom. It's called another name, but it's just a bigger snowball of particles. They start with the smallest particle, 1840, and before 1840 it just falls apart into a million pieces. And that's why if you put a spark right next to a hydrogen, boom, it explodes like a bomb. All of these pieces fall apart because they say, no, now we're unstable with it. You just blew us all into pieces. All the particles go crazy. If you just had one of these and you threw a spark at it, why would you think it'd explode? There's nothing to do. It's just one little piece. We're going to go through this and you're going to understand it. Like I said, you're 8 years old, 10 years old, and up should have really no trouble with this. Because what was understood before is totally wrong. The standard model, they call it, which we're going to go into, is just based on these big particles, and they cannot figure out what is right because they started from the wrong basis. And you cannot start from the wrong starting point and get to the right end result. You have to find out, what are we really dealing with? And we're dealing with this, not this. Okay, now you tell me what makes sense. Remember, I just showed you what my claim was. These are the mass units, which means how much things weigh. And an electron has to weigh something. They show it weighing nothing whatsoever because it's so small that they just forget about it. And here's the real key that's funny, because a neutron and a proton are basically the same weight, they say, except it's not true. If you really figure it out, the neutron is 1 electron bigger than a proton. Here's the real weights. The electron mass is this atomic mass unit. It's 1 electron and it's negative. Okay, so here we got electron, negative, yes. It's in the orbitals, yes, but it's also in the nucleus, because nothing more than a nucleus is a ball of these little particles, not big chunks. Now, a neutron, they say, has no charge whatsoever, and it has a mass exactly the same as a proton. Why would it have no charge? And it is in the nucleus, yes. Well, here's what a neutron is. It consists of an equal number of electrons. So there's 1840, so it's neutral. It's not, it doesn't attract and it doesn't push away. It's neutral, 1840. If we lost 1 electron and brought us down to the proton mass, which these are the correct masses. A neutron is 1 because that's what's considered the atomic mass unit 1. a proton is one less electron than a neutron. How could that possibly be? If they were big one particles all by themselves, they're not. And they know they're not. And in addition to that, you have nuclear decay and you have isotopes and ions. What does that mean? Ions have extra electrons attached to them that shouldn't be there. But they're in there and they say, well, that's an ion. Well, what does that mean? It means it has an extra electron. How could it have an extra electron if it's inside of the proton? It doesn't make any sense. Nothing makes sense. That's why it doesn't make sense. So you have to go to electron flood theory, or electron flood model, which is my model. Now, again, you got kids, 12 years old, they should understand this. Instead of this one gigantic particle, all right, don't forget, that would be a neutron, or well, this would be the proton. All right, and this would be an electron. Instead of that being what a hydrogen is this. All right, and each one of these is an electron, and the muon is attached to it. So this is magnetic. All right, these are magnets. And that's exactly what is, there's a positive side and a negative side. And there's 1,839 of these make one proton. All right, so a hydrogen literally is 1,840 here. All right, it makes it neutral in the center, and it does not want another one. It says, I don't want you coming in here. It may have 1841, so it gives it a push away, so that it gives it more of a oomph. And it will go to 1842, 1843. Those are called isotopes. And they know this, but they can't account for them, so they just never talk about them. Now, I go on to show more about what atoms really look like. The dark side of the atom, which is called a muon, goes to the center. And all of the explosive particle parts, which is the electron portion, they're explosive. The muon side of the electron, and this is an electron. Now you see it as one ball, but if you saw two balls like that, that's really what I'm claiming is one of those would be dark and one of them would be explosive. And that's what you have, an electron and a muon. And this is what we consider to be an electron. It's not. Well, it is, but we never knew about the dark side. And that's dark matter. That's dark matter and gravity. And I show this in our experiments. So don't forget, there is no gigantic balls of protons and neutrons. There's nothing more than big balls of little magnets. That's all it is. And the one side goes more to the center, and it's coated by the explosive parts. So at rest, this ball would be like this, but all we would see on the outside is the ones that want to get away from each other. And the black parts go right to the center, and that's what is like almost like a black hole. And I'll explain this. It is basically the same thing as what they're looking for: black holes, dark matter, all of the things, these neutrinos, muons, bosons, all of that we're going to go over. I know it's a lot of big words. They mean very little. All it means is, I'll show you what it means. But there's three different colors that appear to be what are their power ranges. And the red is not so strong. The blue is very strong. The green is in the middle. We're going to go through this, but so far, I think I'm going to stop it at this right now, and I am going to ask for people to ask questions. If you have questions regarding what I just presented, go back through it several times, because this is brand new. Nobody knows about this. Yale doesn't know about this. Nobody knows about this because they haven't been listening. I've been trying to push it on everybody. When I went to the University of Geneva, I showed it to them, all of my experiments and stuff, and they were very impressed, and they said, oh, this is great. We'll follow you. I said, you're going to follow me? I said, why don't you guys do something about this? And that was it. I never had any more conversations. Electron flood model works. Okay, just so you understand, you can get educated for yourself. You don't have to pay these people. They'll put these things online for you. They just won't give you a degree and a piece of paper that says you know what you're doing unless you pay them. And then to know what you're doing means that you know how to say what they told you to say. And all they're going to tell you to say is what someone told them to say. You will learn nothing. So basically every college has a presence now online, and they show you courses. I go to Coursera. I took courses at University of Geneva, particle physics. I've taken genomics at, what is that one? Johns Hopkins. I've taken chemistry at Rice. I've taken all kinds of stuff, and it's free. And I don't care about getting a degree on this stuff because they'll let you go to anywhere. And they send me every couple of weeks. I get all kinds of new courses that they recommend for me based on what I have looked at before, photons and quantum and all these different things. But they also have all these new courses that every day you can find out something new from there because it changes every day. So don't lock yourself into a school and end up paying through the nose for the rest of your life for something that's not going to be correct. And I'm telling you right now, very shortly, everything that you have learned in the past is going to be completely overturned, as I will show you. Uno momento. Okay, my friends, when I say everything's going to change, everything will. As soon as mud fossils gets realized and electron flood theory gets looked at, then it's all over, because the things that they told you just aren't true. We have ancestors that were no-toes. And we had giants, and I have them, they're DNA certified, and we have ones just like us, same size as us, that are petrified too, in mud fossilization. DNA certified CAT scans, anatomists, chemistry, recreated process, everything's done. It's time to look at this and look at everything that I'm presenting, because once I realized that there was no interest in reality in like Yale and so forth, because I brought all this stuff to Yale, they just won't even talk to me, and no university will talk to me. So I'm going to you. All right, let's learn.